AB Calculus Note Card 8, Average Rate of Change. This is the 8th video lesson in the Note Card series, developed from the work of Stacy McMullen, formerly the Dallas Independent School District. And average rate of change. The average rate of change of a function over an interval is called a difference quotient. And so there are different ways of describing this difference quotient. You have the amount of change divided by the length of the interval, delta y over delta x. The one that I've tended to use a lot here in my class is this f of b minus f of a over b minus a for that closed interval, the slope of a secant line through 2 points. And then we have the difference quotient mentioned here, where you have x, the value of x, or the input value, changing by h. And then, so anyway, different ways of describing the same thing. Often this little acronym will come out for average rate of change, AROC. So let's go ahead and work out a few problems related to average rate of change. 1. An experiment of population of bacteria. Find the average rate of change from P to Q and draw in the secant line. And so we have P to Q here, and we can actually, I'm going to draw in the secant line first. So secant line is going to be something like this. Okay, there we go. So that would be the secant line, not a very well drawn line, but well enough. And find the average rate of change. Well, your average rate of change is going to be f of b minus f of a over b minus a. And so we can say, okay, this is going to be, we have q is going to be this 45 comma 340. So we can call this b comma f of b. And this other point down here, we can call this a comma f of a. And then we can just work that out. So our answer for this could be 340. That's f of b. F of a is 150. And then we have over b minus a, which could be 45 minus 23. And I'm going to resist the temptation to work out the arithmetic here because that's not necessary. And the units are crucial here. And so that's going to be number change. That'll be the number bacteria or bacteria growth per day. Okay, number of bacteria per day. So growth per day, that's that one. Next problem. Again, double asterisk, actual AP test problem. Traffic flow, FT is defined as the rate at which cars pass through an intersection measured in cars per minute and T is in minutes. The traffic flow intersection is modeled by the function F defined by FT equals 82 plus 4 sine T over 2, for T being between 0 and 30. What is the average rate of change of the traffic flow over the time interval from 10 to 15? So for that, we're going to get our, I'm going to just articulate here below first. So our average rate of change is going to be equal to f of 15 minus f of 10 over 15 minus 10. So, and that's going to be, what are units going to be? Well, the flow rate, traffic flow, cars pass through an intersection, cars per minute, and T is in minutes. So it's going to be the change It's going to be cars per minute. Per minute. It's going to be cars per minute. Per minute. Sometimes you can write that as squared. So let's go ahead and look at this. Go to the calculator, and I'm going to get the calculator the right dimension to see it entirely here. Okay, we are in our calculators in radians here, and that's what we need to have for proper calculation. So we're just going to put this in here. I'm going to store a value. We're going to have f of b over f of a. So I'm going to say b. Well, we're going to use t since t is used here, right? T storage control. I'm going to use the number first. So 15 control var t. So we stored 15 for t, and now the equation here, function 82 plus 4 sine, and then we have t over 2 so that's going to be 85.752. Okay, and next we're going to store in 10 control var t. Okay, same thing, 82 plus 4 sine t over 2 . So we get 78.1643. So we can say 85.752, which is f of b, minus f of a. Well, I'm just going to put control A and S for last thing calculated and get 7.5877. Over 15 minus 10, we know it's going to be 5, and that's going to be cars per minute squared. Now the initial function was in cars per minute, and so the rate of change of a function's originally cars per minute is going to have to be cars per minute squared or cars per minute per minute. So that will be our answer here for this problem. And the last one we're going to look at is this one. Use the table below where f of t is a population and t is time to estimate f prime of this little tick here. It means derivative of 1870, and interpret the meaning of your answer. Well, AP test standards are that if you have a value, in this case, in 1870, you had exactly 38.6 million. The one I would like to use is on either side of 1870. So I'd like to consider like 1880 would be B, 1860 would be A, and so you would have f prime of 1870, which is really an estimate. So I'm going to put EST of f prime of 1870 equals f of 1880 minus f of 1860 over 1880 minus 1860. So that is going to be 50.2 minus 31.4 over, that would be 20 years. I'll just put 20. And that's going to be population. So this would be population, and that's a population in millions. So growth in population, and the units would be millions per year. Now, also with AP standards, we could have used 1860 and 1870, or we could have also used 1870 and 1880. To me, logically, it usually works best on either side of the value in question. So anyway, I hope this is helpful to you. Good luck, and thanks for viewing.